Hi, this is Stu Schwartz from MasterMathMentor.com. This is video Precalc 04B, and the topic is the graphs of trig functions continued. In the previous video, we were given equations and we were asked to either graph it or determine all the features of the graph. Now we reverse the process. You will be shown the graph of a trig function, and your job is to come up with the equation of the trig function. We found that the general equation of sinusoids were y is equal to d plus or minus a sine of b quantity x minus c, or y is equal to d plus or minus a cosine of b quantity x minus c. We found by altering a, b, c, and d, we changed the behavior of the graph. So now, reversing the process, we look at the behavior of the graph and subsequently find a, b, c, and d. So our job is threefold. First, we have to determine whether we're going to use the sine or cosine form. We're going to have to decide whether we're going to use a plus or minus. And then finally, we will find A, B, C, and D and put it all together into one equation. Here are some things we must determine in order to generate the equation of our sinusoid. First question, is it a sine or cosine curve? This is not quite obvious, and we will look at this in more depth in the next slide. But for right now, we will use the generalization that if the curve starts in the middle and then goes up or down, we will consider it to be a sine curve. If the curve starts at the high point and goes down, or at the low point and goes up, we will consider it to be a cosine curve. This curve starts in the middle, and we will call it a sine curve. Next, we have to determine whether it is a plus or minus. And in order to do that, we have to ask whether it's a normal or reverse curve. A normal sine curve starts in the middle and goes up, while a reverse sine curve starts in the middle and goes down. A normal cosine curve starts at the top and goes down, while a reverse cosine curve starts at the bottom and goes up. This curve starts in the middle and goes up, so it is a normal curve, and we will use a plus sign. Next, we need to find the axis of symmetry, which will be our d value. In the case of sine curves, the axis of symmetry is obvious. It's where the curve starts. But sometimes with cosine curves, it's not obvious. The best way of finding it is the average of the high value plus the low value. In this case, the high value is 5, the low value is -1, and the average of that is 1/2 of 5 plus -1, which is 2. And that is the value of D. Next, we need to find the amplitude. Whatever the amplitude is, that will be the value of A. The amplitude we know is the height of the curve above its axis of symmetry, which we just found to be 2, and the height of the curve is 5, so that makes the amplitude 3. Therefore, A is equal to 3. Next, you will find the period of the curve by inspection. Usually, the graph will actually show you one period of the curve. If not, you want to find the value of x where the curve starts to repeat. We use the fact that the period is equal to 360 degrees divided by b, so therefore b is equal to 360 degrees divided by the period. In this case, the period is 180 degrees, and therefore b will be 360 degrees over 180 degrees, and therefore b is equal to 2. Finally, we would like to find any horizontal shift, which will give us our C value. If the curve is shifted right from 0 degrees, that means C is positive. If the curve is shifted left from 0 degrees, that means C is negative. In this case, there is no shift, and therefore C is equal to 0. Finally, we put it all together. We end up with y is equal to 2 plus 3 sine of 2x. It is recommended for these problems that you then pull out your calculator and graph them in degree mode. You should graph them with your x min, x max, y min, y max to be exactly what you see on the picture that you were given. And you should, if you are correct, see an exact match of the curve. The equation of this graph is hiding beneath the graph itself. Take a few seconds and look at the graph and decide what you believe the equation that generates it is. Most likely, you thought that this was the simple graph of y is equal to cosine of x. It well may be, but that's not what was generated. This is the graph of y is equal to the sine of x plus 90 degrees. How is that possible? Well, we see a graph of y is equal to sine of x in green. If we shift that curve 90 degrees to the left, we get y is equal to sine of x plus 90 degrees. And that gives us the cosine curve. So what we find is that there is more than one way to generate the graph of a curve. For instance, look at the sine curve in green. Let's translate it 90 degrees to the right. That will take, at x is equal to 0, our value will be -1. If we then reverse the curve, we end up with a cosine curve. So y is equal to negative sine of x minus 90 degrees is the same as cosine of x. Again, look at the sine curve in green. Let's now shift that 270 degrees to the left. That will give us the point 0, -1. If we reverse the curve, we have the point 0, 1, and we are left with the cosine curve as well. Let's look at the cosine curve in red. If we translate that 180 degrees to the right, the value at x is equal to 0 again is -1. And if we then flip that curve across the x-axis, we then reverse it, and we have y is equal to negative cosine of x minus 180 degrees is also cosine of x. You may now understand that there are other ways of representing a trig curve. In fact, any trig curve can be represented in an infinite number of ways. However, that does not answer the question of why we should take a simple curve like y equals cosine of x and make it complicated. In general, we will not do this. However, there are times that using another representation of a curve will make the process of generating the equation a little bit easier. For instance, let's look at the equation we just worked on the previous page. We found that this equation was y is equal to 2 plus 3 sine of 2x. We called this a sine curve because it started in the middle. However, sometimes it is more convenient to think of this as a cosine curve that has been shifted. In this case, it has been shifted 45 degrees to the right. And therefore, we can also describe this curve as 2 plus 3 cosine 2 quantity x minus 45 degrees. You might ask, why do we do that? It is easier sometimes to find the high point or the low point of a curve. I liken it to finding the midpoint of a river. Sometimes it's not clear if you're swimming in a river what is the middle of the river. But finding the edge of the river on either side is usually very, very easy. So sometimes we will find that it is easier to always consider our curves to be cosine curves that may or may not have been shifted. In exercise 7, there are 6 graphs, and you are to use the technique that we just explained to find the equation of each. Obviously, there are infinite number of solutions. We choose to use the simplest one using the cosine function. However, any one that you come up with is okay. You should verify it using the calculator, using the technique shown. In number 1, d is equal to 1 plus negative 3 divided by 2, which is negative 1. The amplitude is 2 as it rises 2 units above the axis of symmetry at negative 1. The period is 360 degrees, making b equal to 1, and there is no phase shift if we are considering this to be a cosine curve. Therefore, our answer is y is equal to negative 1 plus 2 cosine of x. B is a good example of why it is a good idea to consider all curves to be cosine curves. If we consider it to be a sine curve, it is not clear where the axis of symmetry is. However, the best way of finding the axis of symmetry is finding the high point plus the low point divided by 2, which is 3 plus negative 3 divided by 2, and the axis of symmetry is simply the x-axis, making d equal to 0. The height of the curve above the x-axis is 3, and that is the amplitude, and therefore a is equal to 3. The period is still 360 degrees, and b is equal to 1. We can consider this curve being shifted to the right 120 degrees. And therefore, the graph of this is y is equal to 3 cosine of x minus 120 degrees. In 7c, again, we will take the approach that this is a cosine curve. The d value is the axis of symmetry, which is high plus low divided by 2, which is 2. And the amplitude is 1, making a equal to 1. The period is 120 degrees, and therefore b is equal to 360 over 120, which is 3. And if we are considering it to be a cosine curve, then c is equal to 90 degrees. Therefore, our curve is y is equal to 2 plus cosine of 3, x minus 90 degrees. However, you could think of this as a reversed sine curve, which has no shift. And probably it is easier to think of this as y is equal to 2 minus 3 sine of x. In D, you may think of this as a cosine curve that has been shifted 360 degrees to the right. However, it is easier to think of this as a reversed cosine curve with no shift. D is equal to negative 2.5 plus negative 1.5 divided by 2, which is negative 2. A is the height of the curve above the axis of symmetry, which is 0.5. We will say that A is negative 0.5 because we are reversing our curve. The period is 720 degrees, and therefore B is equal to 360 over 720, which is 0.5, and we are saying that there is no shift. Therefore, the curve's equation is y is equal to -2 minus 1/2 cosine of 1/2 x. E is easy. At x is equal to 0, the curve is at its maximum height, and therefore this is simply a cosine curve with no shift. D is 5 plus -3 divided by 2, which is 1. And the amplitude is 4, as the curve rises 4 units above 1. The period is 90 degrees, and therefore B is equal to 360 divided by 90, which is 4. And there is no shift. The equation is y is equal to 1 plus 4 cosine of 4x. F is similar to E in that we are still being shown the high point at x is equal to 0. Don't concern yourself with what you see to the left. It is the high point that we're interested in, and therefore this is a cosine curve that has not been shifted. Our D is 0 plus -1 divided by 2, which is -1/2, and the height of the curve above that is 0.5. The period is 180 degrees. We are showing one period of the curve, and therefore B is equal to 360 over 180, which is 2. There is no shift. Therefore, the answer is y is equal to -0.5 plus 0.5 cosine of 2x. Suppose we had a sinusoid that was passing through the points 1, 3, 4, 5, 7, 3, 10, 1, and 13, 3 as shown. We would like to find the equation of that sinusoid. The first thing you must realize is that we are no longer working in degrees. Our x values are pure numbers, which suggests that we must be using radians. This will not affect how we do the problem, however, but we realize that x must be now, instead of degrees, radians. Next, we will assume that our equation is y is equal to d plus or minus a cosine of b quantity x minus c. As we've seen, it is usually easier to consider a curve a cosine curve than a sine curve. So, our job is to find a, b, c, and d. We will start by finding the phase shift. That will be the distance from the y-axis to the high point. In this case, the curve has been shifted 4 units to the right, and therefore c will equal 4. Next, we will find the axis of symmetry, d. It is clear that it is y is equal to 3, but if you're not sure, it's high plus low divided by 2. 5 plus 1 is 6 divided by 2, which is 3. That makes d equal to 3. Next, we need the amplitude, which is a, the height of the curve above its axis of symmetry. This is clearly 2. Finally, b. We can tell that the period is 12. It starts at x is equal to 1 and repeats when x is equal to 13. So the period is 13 minus 1, which is 12. And therefore, b is now, instead of 360 degrees, it is 2 pi over 12, or pi over 6. So putting it all together, our equation is y is equal to 3 plus 2 cosine of pi over 6 times the quantity x minus 4. When you put this into your calculator, be very careful with the parentheses. Note that we need the first parentheses around the cosine, and then a parentheses around the pi over divided by 6, and then a parentheses around the x minus 4. It is not necessary to close the cosine parentheses, but we must have a double parentheses or you will get an incorrect curve. There are other equations that will fit. For instance, we can think of this as a sine curve shifted 1 unit to the right, or y is equal to 3 plus 2 sine pi over 6 quantity x minus 1. We could also think of it as a reversed cosine curve shifted 10 units to the right, and therefore y is equal to 3 minus 2 cosine of pi over 6 quantity x minus 10. In example 8, we have another set of 5 points, this time in green, and we would like to find the equation that generates it. Setting up our table A, B, C, and D, if we consider this to be a normal cosine curve, we will say that it has been shifted 5 units to the right and C equals 5. Our axis of symmetry D is high plus low divided by 2, which is 11 minus 12 divided by 2, or negative 1/2. Our amplitude, the height of the curve above its axis, is 11 minus negative 0.5, or 11.5. Our period is 13 minus negative 3, which is 16, and therefore b equals 2 pi over the period, which is pi over 8. So putting it all together, our answer is y is equal to negative 0.5 plus 11.5 cosine of pi over 8 quantity x minus 5. There are other answers. Thinking of it as a reversed cosine curve, we get y equals negative 0.5 minus 11.5 cosine pi over 8 x plus 3. Thinking of it as a normal sine curve, we get y is equal to negative 0.5 plus 11.5 sine pi over 8 quantity x minus 1. And thinking of it as a reversed sine curve, we get y is equal to negative 0.5 minus 11.5 sine pi over 8 quantity x minus 9. Remember, you only need to come up with one of these equations. Simple harmonic motion in physics is repetitive movement back and forth through an equilibrium or central position so that the maximum displacement on one side of this position is equal to the maximum displacement on the other side. The time interval of each complete vibration is the same. There are a number of examples of simple harmonic motion. Let's look at some of them. Swings that we see in the park are an example of simple harmonic motion. The back and forth repetitive movements of the swing against the restoring force of gravity is the simple harmonic motion. A pendulum is also an example. The pendulum oscillating back and forth from its mean position is an example of simple harmonic motion. Bungee jumping is an example of simple harmonic motion. The jumper oscillating up and down is undergoing simple harmonic motion due to the elasticity of the bungee cord. Ocean waves, due to the tides, form crests and troughs. Contrary to normal thought, it is not the water that is moving, but energy in simple harmonic motion. The back and forth movement of the cradle is caused due to a single push and is maintained by the principle of simple harmonic motion, causing the baby, or in this case the cat, to sleep. The process of hearing is impossible without simple harmonic motion. The sound waves that enter our ear causes the eardrum to vibrate back and forth. Example 9 is our first example of harmonic motion. Suppose Tarzan is swinging back and forth on his grapevine. As he swings, he goes back and forth over the riverbank, hovering alternately over land and water. Jane decides to mathematically model his motion and starts her stopwatch. Let t be the number of seconds the stopwatch reads, and let y be the number of feet Tarzan is from the riverbank, not his height. Assume that y varies sinusoidally with t, and that y is positive when Tarzan is over land and negative when Tarzan is over water. The graph you see below is not the path of Tarzan. Neglecting height, his path is a straight line. Over water, over land, over water, over land. The graph you see describes his possible distance from the riverbank, the t-axis, with respect to time. For instance, at t equals 0, he is 15 feet over water. At t equals 3, he appears to be crossing the riverbank, and at t equals 6, he appears to be the furthest out over land, which is 15 feet. So we are looking at his position relative to the riverbank with respect to time. Continuing, Jane finds that at 2 seconds, Tarzan is at one end of his swing 23 feet from the riverbank over land, and at 5 seconds, Tarzan is at the other end of his swing 17 feet from the riverbank over water. We set up a table with values of t and y, and we have 2 points. We know that positive values of y is when Tarzan is over land, negative values when he is over water. So we have the points 2, 23, and 5, negative 17. Since this is a harmonic motion problem, we see that it takes 3 seconds for him to go from his furthest position over land to his furthest position over water. So therefore, it must take another 3 seconds to get back to his furthest position over land. So we have a new point, 8:23. We show the 3 points on the accompanying graph. So in another 3 seconds, we are back out at negative 17, and in another 3 seconds, we're back out to 23. So we have then 2 new points, 11, negative 17, and 14, 23. We show those points on the graph as well. Since we know our curve will be in the form of y is equal to d plus or minus a cosine of b, quantity t minus c, let's go through our work to find c, d, a, and b. C is how far the cosine curve is shifted to the right, which is 2 units. D, which is the axis of symmetry, will be high plus low divided by 2. 23 minus 17 divided by 2 is 3. A is the amplitude, the height of the curve above the axis of symmetry. The axis of symmetry is at 3, and the curve goes up to 23, therefore A is 20. The period is 6. It takes 6 seconds for Tarzan to go from this furthest position over land back to the furthest position over land. So since the period is 6, b is 2 pi over 6, which is pi over 3. So putting it all together, our equation is y is equal to 3 plus 20 cosine of pi over 3, quantity t minus 2. We show the graph with the graph passing through all 5 points. We also show the axis of symmetry at y is equal to 3. Note that there are many other equations that will fit this situation. We only need to come up with one of them. We can now answer some questions about the situation we just created. First, where was Tarzan when Jane started her stopwatch? We need to find the value of y at 0, or y of 0. That is 3 plus 20 cosine of negative 2 pi over 3, which is 3 plus 20 times negative 0.5, which is negative 7. Interpreting using the graph, he is 7 feet over water heading towards land. You could also do this on the calculator, assuming that y1 contains your equation. From the home screen, use y1 of 0, and you should get negative 7. Question B reads, find the smallest value for t when Tarzan was directly over the riverbank. As we can see from the graph, Tarzan is over the riverbank an infinite number of times. We want the smallest value, which represents the orange dot. So we set 3 plus 20 cosine of 2 pi over 3 quantity t minus 2 equal to 0. And on the calculator, we will find the 0 of that function. And we get t is equal to 0.356 seconds. Question C reads, how long is Tarzan over water within one of his full swings? We merely want to find the distance between the two purple dots on the graph. That is when he first enters the water and then when he exits being over water. So again, we set the function equal to 0 and find the two zeros. He enters the water at t equals 3.64 seconds, exits the water at t is equal to 6.36 seconds, and therefore he is over the water for 2.71 seconds. D reads, it is safe for Tarzan to fall only when he is at least 10 feet from the riverbank over water. What percentage of time will it be safe for him to fall? On the graph, using the dark red dots, we see the two times that he first is approaching being 10 feet from the riverbank and then leaving 10 feet from the riverbank. So we need to find those two times and subtract them. So we set 3 plus cosine of 2 pi over 3 quantity t minus 2 equal to negative 10. We use the intersect feature of the calculator, and we get t is equal to 4.18 seconds, and t is equal to 5.82 seconds. Subtracting, we get 1.64 seconds. And within one period, which is 6 seconds, that means that he is safe for 1.64 over 6, or 27.33% of the time. Number 10 reads, Mark Twain sat on the deck of a river steamboat. As the paddle wheel turned, a brightly painted yellow dot on the paddle blade moved in such a way that its distance from the water's surface was a sinusoidal function of time. When the watch read 4 seconds, the dot was at its highest point, 16 feet above the water's surface. The wheel's diameter was 18 feet, and it completed a revolution every 10 seconds. We put the given information, the distance from the dot to the water's surface as 16 feet, and the diameter of the wheel as 18 feet, on the diagram. We realize that t equals 4, y has to equal 16, and since it completes a revolution every 10 seconds, it will also be at 16 when t equals 14 and t equals 24. Since the diameter of the wheel is 18 feet, it will be at its lowest position, halfway between 4 and 14, which is 9 seconds. And the lowest position will be 2 feet below the water's surface, or negative 2. So we have the two additional points, 9, negative 2, and 19, negative 2. We now need to find the values of a, b, c, and d for our cosine equation. Our cosine curve is shifted 4 units to the right, and therefore c equals 4. The axis of symmetry is high plus low divided by 2. 16 minus 2 divided by 2 is 7. A is the amplitude, the height of the curve above the axis of symmetry. The axis is 7, and the curve goes up to 16, so A must equal 9. The period is 10 seconds, and therefore B equals 2 pi over 10, or pi over 5. Therefore, the equation that describes the motion of the yellow dot relative to the water surface is y equals 7 plus 9 cosine pi over 5 times the quantity t minus 4, where t is measured in seconds. Using the calculator's graphic abilities, there are 3 questions we can easily answer. The first question is, how far above the surface was the dot when Mark's stopwatch read 5 seconds? All you need to do is to find y of 5. If your equation is in y1, then you use vars, y1 up parentheses 5, and you get an answer of 14.28 feet above the surface. Question C asks, what percentage of time was the dot below the water's surface? We need to find when the graph dips below the x-axis. The first 2 times that occurs is at t is equal to 7.92 and then 10.08. We subtract them and divide it by 10 because that is the length of a period, and we get 21.6% of the time the dot is below the water's surface. D asks, when was the first time that the dot was at the surface of the water? Was it entering or emerging? If you look at the graph very carefully, you will find that at t equals 0, the y value is just barely negative. So at t equals 0.08 seconds, using the 0 function on the calculator, we find that it is at the surface and it is emerging from the water. 11 reads, in various cities at differing latitudes, the longest and shortest days, in terms of times of daylight, are shown in the table to the left. The longest day of the year is called the summer solstice and usually occurs around June 20th. Assuming that the curves that describe daylight yearly in cities is sinusoidal, create a general equation that would describe the daylight based on the longest and shortest days of the year. And we see in our table 4 cities, Panama, Miami, New York, and Anchorage, and these cities are in order from the distance from the equator. We first convert the hours and minutes to decimal hours. You can do this on the calculator using the second angle menu. Next, we want C, D, A, and B for all cities. This seems like a lot of work, but we find that all cities will have the same C, D, and B. We start with C, which is the horizontal shift to the maximum value. We know that the maximum value for each city is on June 20th, the summer solstice. June 20th is the 171st day of the year. So for all cities, C will equal 171. For D, the axis of symmetry, it is 12 for all cities, as the longest day plus the shortest day always adds to 24. And the period is 365 days, so for all cities, B equals 2 pi divided by 365. So the only variable that actually is different for all cities is A, the amplitude, the height of the curve above the axis. For Panama, it is 0.53. For Miami, 1.37. New York, 2.57. And Anchorage, 7.35. So the number of hours of daylight, y, for each city is 12 plus a cosine of 2 pi over 365 times the quantity t minus 171. Since a, the amplitude, is found by taking the longest day minus 12, we have y is equal to 12 plus quantity longest minus 12 times the cosine of 2 pi over 365 times the quantity t minus 171. We show the graphs of the 4 cities in color: Panama in blue, Miami in red, New York in green, and Anchorage in purple. Let's add 2 entries to the table. First, Quito, Ecuador. This city lies practically on the equator, and the longest day is 12 and the shortest day is 12. Therefore, the only thing that changes is A, and now A is 0. There are no cities directly on the North Pole. The closest is about 600 miles away. But if there were, the longest day would be 24 hours and the shortest day would be 0. That would make A equal to 12. So we now can show these 2 graphs, Quito in pink and the North Pole in brown. And we find that Quito is nothing more than a straight line, while the North Pole will show the largest amplitude of all the cities. Quito, Ecuador, lies exactly on the equator. That means that every day in Quito is the same: 12 hours of daylight, 12 hours of night. So the North Pole stays in pretty much full sunlight all day long throughout the summer season. That's why it is called the land of the midnight sun. And of course, the darkest time of the year in the North Pole is the winter solstice, approximately December 21st. There has been no sunlight or pretty much even twilight since early October, and the darkness lasts until the beginning of dawn in early March. Part B reads, an astronomer needs at least 10 hours of darkness for a long photographic exposure of the night sky. In each city, on what days of the year are such long exposures possible? A day has 24 hours, so 10 hours of night corresponds to 14 hours of daylight. So we need to solve the inequality y less than or equal to 14 for each of the cities. It should be clear that for Panama, Miami, and Quito, this inequality is always true, which means that we can be assured that on any night of the year, we will have at least 10 hours of darkness. But for New York, Anchorage, and the North Pole, we have to find the days of the year that such a photograph is allowable. To do this on the calculator, we graph y equals 14, and for New York, we find the intersection points between the 2 curves. We find the intersection points are t equals 132 and t equals 210. The inequality y is less than 14 is true from day 0 to day 132, and then day 210 out to day 365, which means that we can take our picture for all days except from May 12th to July 29th. We do the same for Anchorage, but get the 2 values of 96 and 246. which means that we can take the picture in Anchorage for all days except between April 6th and September 3rd. The North Pole is not that much different from Anchorage. Our days are 89 and 253, which means that we can take our picture at the North Pole for all days except from March 31st up to September 10th. We have spent an inordinate amount of time on the sine and cosine curves. What about the other trig functions, tangent, cotangent, cosecant, and secant? Those have graphs as well, and we will now investigate them. First, we have the graph of y equals tangent of x. Notice that the period of this curve is 180 degrees, or pi radians. And this curve, along with the others, have asymptotes, vertical lines that the curve approaches but never touches. This has asymptotes at x is equal to 90 degrees and x is equal to 270 degrees. We know that because there are no values for the tangent of 90 and the tangent of 270. Next, we have the graph of y is equal to cotangent of x. It is similar in that the period is 180 degrees, or pi radians. But this has asymptotes at x is equal to 0 degrees, x is equal to 180 degrees, and you could also say at x is equal to 360 degrees as well. Since the cotangent function is the reciprocal of the tangent function, when the tangent function increases, the cotangent function decreases. The shape is similar. Next, we have the graph of y is equal to cosecant of x. The period of this graph is 360 degrees, or 2 pi radians. And there are asymptotes at x is equal to 0, 180, and 360. This graph is the reciprocal of the sine function. So while the sine function lives between -1 and 1, the cosecant lives from 1 to infinity and from -infinity to -1. As the sine function goes up, the cosecant function goes down. As the sine function goes down, the cosecant function goes up. Finally, we have the secant function, which is similar in shape to the cosecant function. Its period is 360 degrees, or 2 pi radians, and this has asymptotes at 90 degrees and 270 degrees. Again, the secant function is the reciprocal of the cosine function. So while the cosine function lives between y equals -1 and 1, the secant function lives when y is greater than 1 or less than -1. Notice again how it is related to the cosine function. When the cosine function in green goes down, the secant function in blue goes up, and vice versa. While we could do transformations of these curves, as we did with the sine and cosine function, they don't appear in many real-life applications to make it worthwhile going through the process. And again, we can always graph these functions on our calculator. We would graph the cosecant function by saying y is equal to 1 over the sine function, and the secant function, which is 1 divided by the cosine function.